Hello everyone, I am Tiantian Liu. I just graduated from University of Pennsylvania. Today I'm going to present our work FEPR as a fast energy projection method for real-time simulation of deformable objects. Simulating deformable objects is hard. In particular, time integration, which discretizes and solves equations of motions, has been a central challenge in physics-based animation for many years now. There are a variety of time integration schemes, such as backward Euler, implicit midpoint, BDF2, etc., etc. Those schemes are usually viewed as nonlinear refining problems or optimization problems that can be solved using different numerical solutions. Each integration scheme can be solved by different solvers, resulting in many time integration solutions. The related work of implicit integration methods can be tracked back to Bernhard-Widekind's seminal work on cloud simulation in 1998. This work enables simulating clouds in large time steps, but it also has significant artificial damping. Fast numerical integrators such as projective dynamics have been developed to fit real-time applications, but they still inherit the damping problem from the backward Euler integration. Here we show the artificial damping from backward Euler. You probably can't even see the jello moving, so let me play it again. The unwanted artificial damping here is so strong that already destroys the animation. Methods such as BDF2, implicit midpoint, or adaptive time steppings are used to combat the numerical dissipation. However, BDF2 only mitigates the damping, and the other methods are either too expensive to run fast or have only limited stability. For instance, implicit midpoint, even completely solved using Newton's method, is still unstable. We observed that both damping and explosion can be tracked from the energy. Artificial damping reduces the energy, while explosions quickly inject the energy into the system. Then the question now becomes, can we find or correct an integrator to conserve the system energy? Well, our goal was to cancel the energy fluctuation from the system so that the animation is stable under huge impulsive forces like being hit by the bullet, and the character can stay vivid afterwards. We propose FEPR that not only corrects the energy fluctuation, but also is flexible, that can be combined with a variety of time integrators, and is lightweight, so it can be applied to even real-time integrators. Besides energy, there are other important quantities needs to be conserved for real-world motions, such as momentum and symplecticity. Can we conserve them all? 3 decades ago, Ge and Marston already proved that it's extremely hard to conserve all those 3 quantities at the same time. How hard it is? It needs to be almost the exact solution to conserve them all. If we can't satisfy them all, something up. Symplectic methods preserve the symplecticity and momentum, discarding the energy preservation constraint. Another set of methods violate the symplecticity but conserves both the energy and momentum. Our method FEPR also falls into this category. So how do we solve this problem? This is the axis of time. For a given position xn and a velocity vn, a time integrator gives us a prediction xn plus 1, vn plus 1. These predicted states might violate the energy conservation law, so we correct xn plus 1, vn plus 1 to x star, v star that conserves the energy. And the FEPR is right there as an add-on to correct it. How do we get to the state x star, v star? We would like to change the configuration returned by the integrator as little as possible in order to preserve both energy and momentum. To this end, we first need to quantify distance in configuration space. We do that by measuring the difference in positions and velocities using the weighted L2 norm induced by the mass matrix to obtain proper scaling with respect to mesh resolution. we can now set up a constraint minimization problem in which we seek to minimize the distance to the predicted configuration while satisfying the following constraints. Here, h is a scalar, stands for the energy. We want the energy of the corrected state the same as the energy in the previous state. P is a 3×1 vector, stands for linear momentum. And L is another 3×1 vector, stands for angular momentum. Those momentum constraints ask the final state to stay in the same momentum with the previous state. Simulation works well for systems that are perfectly momentum conserving. For instance, planetary systems in celestial mechanics. But most applications in graphics do not fall into this category. There are many scenarios where momentum actually changed. Think of the free fall example where the momentum changes on the vertical axis, so we need a mechanism for relaxing those momentum constraints. One potential option might be to just drop the constraints, but doing so can lead to large momentum fluctuations with noticeable impact on the animation. Another option would be to use the momenta Pm+1, Lm+1 obtained from the integrator as a constraint target. However, doing so introduces a new problem, as the optimization problem is no longer guaranteed to have a solution. To address this problem, we add two slackness variables S and T into the system. The formulation allows for momentum changes during the projection if necessary, but restricts changes to an interpolation between the momenta of the current and the previous simulation step, by virtue of the two variables S and T. It thereby guarantees the existence of a feasible solution. See, if we set x equals to xn, v equals to vn, which are the previous state, and set s and t equals to 1, the constraints are trivially satisfied. Therefore, we finally choose this form as our constraint optimization problem. It has 6n plus 2 degrees of freedom, where n stands for the number of vertices. It's 6n for positions and velocities and 2 for s and t. It has only 7 constraints, 1 for energy, 3 for linear momentum, and 3 for angular momentum. How do we solve this problem? The optimization problem that we derived has a quadratic objective, which is nice, but nonlinear constraints. Giving rise to this nonlinear manifold shown in this picture, intuitively, for a given starting point returned by the integration scheme, we would like to find the closest point on the manifold. In the other word, a configuration that satisfies the energy and momentum constraints that deviates as little as possible from the predicted state. Knowing that geometric interpretation, let's first aggregate all the unknowns into a single variable q, and denote the objective as a D-matrix weighted square distance function. We call the matrix D because it's a diagonal matrix. Let's also denote our constraints into a simple form CQ equals 0. It is now a 7×1 vector constraint. How can we solve this optimization problem? There are a number of standard nonlinear programming solvers that one can consider, such as sequential quadratic programming SQP and interior points method. We tried several instances of those solvers, both off-the-shelf and homemade ones, and while they can solve the problem successfully, they are way too slow for the application that we target. Ideally, we would want a solver that does not take more time than the integration scheme, and preferably less. Can we solve it approximately but much faster? Here, we are inspired by the work of Gonzalez and colleagues to do the fast projection. The problem is to find the closest point to Qm+1 on a nonlinear manifold CQ equals 0. Instead, we can formulate it as a sequence of linear problems like SQP. For example, we initialize Q0 equals to Qm+1, linearize our constraint C at Q0, and we can find the closest point Q1 satisfying the linearized constraints. We can again start from Q1, linearize the constraint here, and find its closest projection Q2. Note that now Q2 is completely blind of Q0. It only sees Q1 and the linearized constraints at Q1. We keep doing this until we find a solution on CQ equals 0 manifold. Again, the difference between this approximation and the solution of SQP is that our approximation finds a solution on the manifold. It is not necessarily the closest point to Qn+1 anymore. The advantage, however, is that we have converted a difficult nonlinear programming problem into a sequence of small linear systems for constraint projection. And those systems are only 7 by 7 in size because we only have 7 constraints, so solving them is very fast. Since the solution computed with the faster projection is only an approximation of the exact solution, a natural question is whether there are any artifacts arising from this simplification. To investigate the impact of the approximation, we performed a number of experiments, such as this humanoid pendulum example. The left animation was computed using SQP, while the right one is solved using fast projection. If we pause it and circle the difference in red, we can tell they are still different. Qualitatively speaking, they are very similar, and our approximation runs 2 orders of magnitude faster compared to SQP. Let me show some results of our method. Our method fixes artificial damping caused by backward Euler, produces a more vivid jello. The left one is simulated using backward Euler. The right one is the same integrator plus FEPR. Besides preventing unwanted energy loss, FEPR can also alleviate instabilities resulting from unwanted energy gain. Here is an example in which implicit midpoint becomes unstable. Using FEPR on top of implicit midpoint keeps the energy at the same level and thus prevents the numerical explosions. Another welcome aspect of our method is its flexibility. It can be combined with a broad set of integration methods. For example, although BDF2 improves on numerical dissipation compared to BDF1, the motion of this rabbit still decays very rapidly. After FEPR is added to the system, the rabbit moved more vividly. FEPR can work with other mechanical systems such as cloth and to different simulation models such as XPBD. As we can see in this example, FEPR not only keeps the amplitude of the oscillation membrane constant, it also produces more detailed wrinkles. We ran lots of examples in order to assess the performance of FEPR, and we say it's always less expensive than the underlying time integration scheme, up to an order of magnitude for some examples. Although our method improves the energy conservation, it does not improve or change the accuracy of the underlying integrator. To analyze the accuracy of our method experimentally, we simulated a pre-stretched cube with decreasing time steps to produce this graph. As the time step decreases, our method converges to its underlying integrator and produces the same error both locally and globally. We compare FEPR to other energy-conserving methods. Hughes' method preserves energy, but it does not take momentum conserving into consideration. In theory, discrete gradient will preserve energy and momentum if it's perfectly solved. But this is a gigantic if, because in practice, nonlinear refining problem is very hard to solve perfectly. Once the solution is stuck in the local minimum, it explodes. Reducing the time step can make discrete gradient problem easier to solve. Here, the time step is reduced to 10 times smaller, but can still not prevent it from explosion. Our method, FEPR, can produce a stable motion using even a large time step, here at 33 milliseconds. We also compare our method against Su and colleagues' work, showing FEPR is more stable than energy budgeting. To conclude, we propose an add-on FEPR to correct the energy fluctuation of a simulation. Our method is general and flexible that can be equipped with different kinds of integration schemes and numerical solutions. Our method is also lightweight, that can be even applied on real-time simulations. One thing I just want to point out before the end of the talk is the difference between stabilizing integrators Dimitar just talked about and this method FEPR. You probably have the same questions too, so let me answer it in advance. I want to talk about those two methods using different metrics. Flexibility. FEPR is an add-on, as we advertised, that can be equipped upon your favorite integrators and solvers, while stabilizing integrators is more like a standalone integrator. So in that case, I would say FEPR is better at flexibility. Angular momentum conservation. Let's take a look at the spinning cube example that can reflect angular momentum the most. Here, stabilizing integrators is on the left and FEPR is on the right. We can speed up the playback 5 times so we can see the right cube spins faster than the left one. We plot the angular momentum around the spinning axis, and we can see that the blue graph FEPR almost conserved the angular momentum toward the end, while the red graph stabilizing integrators loses it from the beginning because of the blending of backward Euler. So I'd argue that FEPR has a better angular momentum conservation property. Simplicity. Although both methods are simple to implement, since stabilizing integrator only requires one binary search between implicit midpoint and the other integrator, I would say it's simpler to implement compared to FEPR. And those two methods also have comparable performance in most of the cases. Last but not least, we thank the anonymous reviewers and our friends for the insightful discussions, and we thank the funding agencies and companies for their kind support. That concludes my talk today. Thank you.